Good afternoon, everybody. Of course, much like my colleague, I would like to thank the organizers of TNSF to provide me this opportunity and my colleague to transfer the excitement of the science that we do and we are fortunate to be doing to this very young audience and what I would call the scientists and engineers and technologists of the future. I will be talking to you in the next about 45 minutes or so regarding the second half of the prize, of the Nobel Prize, which was shared by two people, the graduate advisor, that is the PhD advisor, Gérard Mourou, and his PhD student, then Donna Strickland, who's, of course, now a physics professor in Canada. Professor Mourou is French, and he's back to France after spending a considerable amount of time in the US. Of course, I'm also from IIT Madras, and I work on the other kind of lasers as against Professor Basudev Roy, who mostly uses continuous wave lasers. Okay, so in some sense, I need to answer this question: what is one half of this prize good for? What was that given for? If you open the OpenNobel.org, they say that they gave this prize for their method of generating high-intensity ultra-short optical pulses. So high intensity, ultra-short, and the method of generation. So these are the three key aspects of this prize. And this very nice view that we also find on the Nobel website itself is very representative of this effect. Is it visible at the back? Okay. In other words, I would say that they got the prize for inventing methods to make very bright femtosecond laser pulses. And I underscore this and add this to my own taste that this technique has no upper limits. You can literally produce pulses or electric fields which are only limited by technology of the current generation, that is ours, and perhaps also financial resources. And this has indeed been pushed up to a considerable extent. Yes. So, what is ultra-short? Ultra-short is an adjective for something very short. For a human being, ultra-short could even mean 10 seconds, in the sense the fastest human being runs 100 meters in 10 seconds. And we can't match that, right? So you step a meter in about 1/10 of a second, right? Whereas a movie goes about in something like 30 to 40 frames a second. And if you go down, you know that my cell phone has frequencies of about 2 gigahertz, which is of the order of, I did some magic. What was that? Okay. This was a mechanical effect, not an electromagnetic one. I just knocked off the wire. So 2 gigahertz is about on the time scale of a nanosecond. Nano is 10 to the power minus 9, or 1 divided by a billion. That is 1 followed by 9 zeros, right? A femto, likewise, is an unimaginable time scale. It is 1 followed by 15 zeros in the denominator, okay, which is extraordinarily short. But are these the shortest man-made events as of today? No, we have produced 1 followed by 18 zeros in the denominator, so-called atto, and very soon we will also be producing perhaps zepto, 1 followed by 21 zeros in the denominator. If you ask the question, what is the age of the universe in seconds, it is of the order of 10 to the 18, that is 1 followed by 18 zeros. So, in that sense, an attosecond, which is 1,000 femtoseconds, is something like a second to the age of the universe. It is that short a time scale. So actually, what can we do in that flash? That's really the question we are trying to ask ourselves, right? There is no upper limit in the sense that this technique can be scaled up to produce higher and higher and higher intensities of light or electric field strengths, as we will see, which when focused can ultimately even break down vacuum. That is, it can lead to pair production. So, but the technique itself can be scaled up to go even beyond the limit from where we start seeing such effects. It is not yet there, but I'm pretty sure that in the next 10 years, we are going to break vacuum with lasers. And if not, you can write an email to me. Maybe let's say 5 years from now, write an email to me saying it still didn't happen. Maybe I will reply to you saying wait 5 more years. And maybe 5 years later, you will say no, it has actually happened. Okay, this is a wager. Let's take it that way. So I'm going to, since this is a prize for a technique, I will try and tell you how these pulses are made and why this technique is important. It's almost unique. And what is the impact of this on science and what its impact is on technology. Its impact on science, these are the shortest events of any kind made by man. We make them, so we control them. We can use them to make so-called molecular movies, okay? And then we are all undergrads here in some sense. So we all go to the physics lab and then crank up a function generator and look into an oscilloscope. The laboratory oscilloscope says, oh, I can look up to 60 megahertz of frequency, okay? But I have a cell phone which is dealing with waves, which is 2 gigahertz, right? So is there an oscilloscope that can see 2 gigahertz? Yes, there is in the market, except that most of us cannot afford it. Institutions can afford it. Can there be an oscilloscope that actually looks at petahertz? Light frequency is of the order of a petahertz. Petahertz frequency is 10 to the 15 or 1 followed by 15 zeros of oscillations in time, as compared to the AC frequency of the light here is about 60 hertz, or it could be 50 or even 100 depending on which country you're living in. Okay, we can even make laser-based accelerators. Okay, the big accelerator in CERN is 28 kilometers wide, whereas we can make accelerators which are even on tabletop, which are of the size of the stage. Maybe 10 years from now, somebody will give a demonstration here. Okay, that's challenging, but it's still feasible. Finally, we can, current laser eye surgeries use this. Microstructuring is very much possible. And perhaps in the near future, we will have fast ion therapy. If you take this road down, take a right, go to Ascendas. Apollo Hospital is very soon going to inaugurate something called a proton therapy center, which is going to be one of its kind in Asia, again to blow apart cancer. It is very foreseeable that this facility, which costs 200 crores, will actually become more affordable because of this kind of laser technology. Okay, but I'm going to take a step back, and since this is about lasers themselves, ask the question, what is a laser? Almost everyone here knows it is light amplification by stimulated emission of radiation. And who taught us what stimulated emission is? It is none other than the great man himself. In the year 1905, the miracle year of physics, he wrote a letter to his friend Conrad saying, I'm going to publish four papers. One of them, he said, is on radiation. And that was the paper. Now, I'm going to ask you a KBC question. It's getting too monotonous, right? So, who invented the laser? Was it Einstein? Actually, theoretically, but it took about 50 years to go from theory to experiment and laboratory realization. So, who invented the laser? Choice, I'm not going to give you. I'm not Amitabh Bachchan. It starts with the same first letter as Professor Govindarajan, T. Actually, my wife guessed it in 2 attempts, though she didn't know. How many American names do you know with T? Tom could be one. Sorry? What is the name of this? Town, yes. What could it be? This is the person, so this is your clue. So the laser he made is actually a very popular gemstone called ruby. So anyway, let me give you the answer and take the 7 crores in my pocket. His name is Theodor Neumann. So he invented the laser, right? But there's a saying, success has many fathers and failure is an orphan. So this success has many fathers. Einstein put this out, showed us that stimulated emission or amplification is possible. Then Charles Townes actually invented the laser in the microwave region, microwaves such as gigahertz. Okay, and his very able colleague Art Shollow, both of them got the Nobel Prize themselves. And finally, at optical frequencies of visible light, ruby laser, which was a pulse laser, was invented by Myman. So a very nice reading about the history is in Townes' own nearly autobiographical sketch. There was another Nobel Prize which is much less recognized, but this went to actually the inventors of optoelectronics, if you wish. One half again, 3 people, one half and one half for the inventor of the IC. And Herbert Kromer actually invented the laser diode, and without which we would not have all the songs that we had in the previous pre-MP3 generation, which was in the form of optical discs. They will perhaps remanifest in some other form sooner or later, okay? But now I'm going to take a quick snap opinion poll of 30 seconds. What is inside a laser? Tell me anything that you think about is inside a laser. And I want the really young colleagues sitting over here an answer from here, at the back, on top, and everywhere else. Yes, madam, you have an opinion what's inside this laser? A diode. A laser has a diode. A very nice point. And what else? What else? It has a diode. She says it has a diode because I just said that there are laser diodes. What else does it have? What else does a laser like this have inside? Or any laser that you can think of? A battery? Yes. And what else? It has monochromatic light. And what else does it have? Mirrors, yes. So you need something like a diode, like a material for a diode, and you need 2 mirrors, right? Actually, I'm going to convince you that that's all lasers are largely about. The rest is technical detail. But if you work it out, you can even get a Nobel Prize, right? But a laser is nothing but this very undergraduate amplifier that you build in your lab, except it does not operate only at kilohertz or megahertz frequencies. It can also operate at petahertz frequencies. So maybe you should have trumped your physics teacher like me sometimes in the class asking, why does not my electronic amplifier work at terahertz, 10 to the 12 hertz? Why does it not work at 10 to the 15 hertz? Why are you stopping at few megahertz, right? We should naturally ask this question. So this same scheme can be applied even to petahertz frequencies. That really is what makes a laser. So you have a gain medium, as it's technically called, or a lasing medium. This is the amplifier part. You have 2 mirrors. That's all there is to a laser. And if you really put them together and your battery that you pointed out, the pump power, then you actually have a laser. So a laser is a gain medium or an amplifier with 2 mirrors or a resonator, which essentially gives us feedback. For example, such a logic is also used in the FM radio that's in your phone. And there it is called a phase lock loop. Okay, so we have this cartoon for a laser, but the laser that we are talking about, such a laser actually, you can say, has a lot of electromagnetic energy stored, and one of the mirrors is partly reflecting, so a wave train comes out. Okay, so this is how literally a laser is made. It stores energy inside this resonator, optical energy, and a part of it keeps leaking out. This is literally what's happening even in this red laser pointer. But the laser that I'm talking about is, okay, I have one more KBC question, and this is of some importance. Who invented the carbon dioxide laser? Okay, we didn't quite get who invented the laser, so this may be like the question for 1 crore of rupees in the quiz show. And I'm asking this with a bit of significance. Carbon dioxide lasers are used for cutting in the industry. Okay, it's an Indian name. That's really why I put it up here. So who invented the carbon dioxide laser? You want to take a lifeline? Okay, it's a Gujarati name. Absolutely right. It is Kumar Patel who invented the the carbon dioxide laser. It works at 10 microns. You can't see it with your eye. It is, for continuous wave lasers, the most powerful laser that one can make. It's also the most efficient laser. It is Kumar Patel. He, in fact, is standing, or in his office, he has this IEEE Medal of Honor. He didn't win the Nobel Prize. He was an engineer. So he got something that engineers get, which is equally honorable, right? Now, this is my laser. How do I make it pulsed? How do I make it boom, 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 like flashlight, like strobe lights that come up in these music shows, dance shows, and whatever not we see these days? You need, over there is something in the electronic circuitry that's making it pulse or flash, right? So you need to put, in this case, also a pulse shortening device, a pulsing device. Make your laser, take 2 mirrors, put the so-called gain medium or amplifier. All the feedback is happening, but then keep interrupting it and keep opening the gate, much like what is done in a astable or a monostable vibrator in electronics, right? So if you take a typical laser and put a pulse shortening device, you would get pulses out, almost like this. Then the oscillation inside is pulsed. Every time it hits this output mirror, a little baby pulse comes out, okay? So all pulse lasers that we know of, predominantly, they don't generate just one pulse on demand. They actually generate a train of pulses like this. That's simply because of the way in which this particular optical device works. The pulse keeps circulating inside. Every time it bounces on the so-called output coupling mirror, you get some light outside. So the main problem that hindered the use of these very short so-called femtosecond pulses, that is 10 to the minus 15 per second. The pulse lasts only that long. The pulse, the width of this little spike is less than a nanosecond. It's a femtosecond. Is that these pulses were very, very weak when they were first invented. That doesn't mean they're useless. They are still very useful. But there was a challenge. How do I amplify these pulses? The problem with amplifying these pulses is the following. What is intensity? Intensity is energy per unit area per unit time, right? So this is what we learn in college. If the intensity of this laser were to be very high, it would drill a hole through this. How do I know this? Even sunlight can do this, right? You sometime either saw or took a lens, you concentrated sunlight, especially in Chennai, it's very easy in the summer, put a piece of paper and it starts burning, right? So inside my laser, if I make things very bright, very intense, the 2 mirrors that I need for producing the laser will burn, and I will no more have a laser. This is a very common sense problem. This prevented scientists from increasing the intensity of the laser. So what Mourou and Strickland, they almost had a very common sense idea. They said, let us decrease the intensity by some form. And as I said, intensity is energy per unit area per unit time, okay? So the per unit time factor becomes very large because all the energy is confined in a few femtoseconds. What Mourou and Strickland said is, okay, in order to reduce the intensity, I really cannot do too much about the size of the beam. I will actually make the beam wider and wider in time. They increased the duration of this pulse or this spike. They made it fatter by 1,000 times or 2,000 times. Thereby, with the same set of optics, they could put a factor of 1,000 more energy, literally, into these pulses. So that these pulses, there is a nano in this, these pulses are typically having an energy per pulse of the order of a few nanojoules or few 10 nanojoules. Whereas here, they could crank this up to a substantial amount, even millijoules of energy could be put into these pulses. But then, we are greedy. We want to have the pulses back very short. So what do? They reverse engineered the same process which stretched this pulse and made it 1,000 times fatter. They reverse engineered it, and after putting the energy, compressed it in one shot to make this pulse much more intense, okay? The process by which they stretched this pulse is called chirping, like the birds chirp, right? So that process is called chirping. So this technique was named chirped pulse amplification or CPA. And this is precisely why they got this prize. Okay. When you do something like that, you might argue, oh, so what? It is just a new piece of technology. It's a new toy, right? So why should it be considered so important? The rest of my talk is essentially going to be dedicated to trying and convincing you that indeed this is very important for science, for technology, and possibly very soon even for humankind in other ways. So now that we have learned about how these laser pulses are made, hopefully, let's look at what kind of science can we do. Science is limitless, boundless, and it's supposed to just be driven by curiosity, right? So why do we need movies in science? After all, we have Netflix and Amazon Prime, right? So why do we need movies in science? Okay, even in the 1800s, when they didn't have a television, people still wanted to have movies, okay? So Leland Stanford, a very rich man, he just like to throw challenges. He said, okay, what is the fastest motion that you had pre-industrial revolution or before industrial revolution? It was the galloping of a horse. After all, machine power is measured in horsepower, right? So he asked, okay, can we ever come with conclusive evidence whether all the 4 legs of a horse ever take off simultaneously from the ground? This is the question he asked. There was no way that one could conclusively devise an experiment in those times to whether say yes or no to this very commonplace observational question. So this challenge was taken up by Edward Muybridge in California. He was a very, very clever man. So what he did is the horse was running, and he basically laid cables like this on the path of the horse. Okay, he had cameras. They did have cameras at that point. So when the horse was galloping, the horse basically kicked a wire. It didn't trip, but it essentially triggered off something that took photographs as it was galloping around. And you can see in this frame over here that indeed all the 4 hooves have taken off from the ground and they don't make contact. Okay, so this is 19th century science, but this gives us a very important lesson as scientists. What you know from statics is not true for dynamics, or there is a lot more information contained in dynamical processes, okay? Whether it is biological cells, which my colleague just spoke to you about, if you can modify the dynamics, you can control things, right? So likewise, to what limit can I control dynamics? If it is on a millisecond time scale, I can maybe try and control the running of a horse, right? Maybe there are better ways to do it than with light. Whereas if I can do it at a billionth of a second, or a millionth of a billionth of a second, which is a femtosecond, then it gives us the possibility to control, take for example this molecule. It is, let us just say water-like but different, A, B, C, or green, red, and blue. If I shine this with light, elementary chemistry tells us that something should happen, and at some point the bond between the red and the blue or the red and the green can break. Okay? We can really split things. As of today, such things are very important because people want to create hydrogen fuels. You want green economies. So hydrogen or water splitting is supposed to be a very, very important thing that people would like to do. I'm not claiming that lasers will answer that environmental challenge. All I'm saying is if you want to selectively break bonds, that is between the blue and the red or the green and the red, lasers can help you do that, okay? By controlling the light that is, the pulses of light that are falling on this, we can selectively break bonds. And if you do that, right, you again go to Stockholm. In the year 1999, Ahmed Zewail, who sadly is no more with us since 2 years, received the Nobel Prize for femtochemistry. This was actually the first Nobel Prize that was given to science with femtosecond laser pulses. Okay, a lot of us know some quantum mechanics, right? So I'll try and use that intuition to tell you how well state-of-the-art steering of chemistry done by physicists, is actually being done by physicists with these kind of lasers, okay? So what do I have here? I have two red dots. These are actually two hydrogen atoms. Hydrogen always comes in the form of molecules. We are even breathing it right now. It is an H2 molecule, right? So it has two nuclei. These nuclei have protons inside them. And the green is the electron cloud. Okay? We were all taught in college that electrons are actually living in orbitals. They are wave functions. They are size. They are mod chi-squares. They are probabilities, probability density functions. All the technical stuff, I just put it in this cartoon in the form of this green cloud over here. Okay? Now, I'm going to shine on this with a laser pulse. This laser pulse has a wavelength of 800 nanometers. Okay? And can you look? It is actually the laser pulse is flipped 90 degrees, just deliberately done. Now, look at the star over here. The laser pulse has an envelope, okay, which is the pulse. And much like in the case of our radio, what is Radio Mirchi's frequency? 93.4. 98.3. What is our audio frequency? What frequency range can we hear? Some kilohertz. 1 to 10 kilohertz. Yeah, I'm pretty bad at acoustics. So let's say 1 to 10. So what does 98.3 megahertz there mean? As against the let's say 3 kilohertz that we can hear. What does it mean? What's the relation between the two? Carrier. So we have two aspects to waves, right? The carrier, and the top is the modulation. Okay? So the pulse is actually always a modulation on a carrier wave which is in the petahertz or 10 to the 15 hertz range. But this pulse is so short that it only covers a few optical cycles under its envelope or cap. With such a short laser pulse, well, actually this was my colleague during PhD. She asked the question, okay, now at the maximum of the cap or the envelope on this side, the undulations inside of the electric field, the maximum of the electric field and the maximum of the envelope match, whereas on this side, where the envelope is a maximum, the field itself, in a sense, does not exist at that point. Okay? There is a sort of asymmetry between the left and the right. If I expose such a laser pulse onto hydrogen atom, okay, this laser pulse will break the hydrogen atom into hydrogen molecule. It will break it into an electron and a charged particle. Let's see that happening. So the pulse is interacting. The electron cloud is essentially sloshing back and forth. In one case, a hydrogen atom without the electron, the proton, reaches the detector. In other case, there is a neutral hydrogen atom going. Now, with respect to the star here, the neutral atom went this way. Okay? Now, let's put the star on the other side and see what happens. I don't have the movie, but exactly the opposite thing happens. Okay? Now, what I did essentially, or what my colleague and several others showed, is that with these kind of laser pulses, I can take the smallest molecule I have and break it in a very controlled way that I want. Okay, you can obviously think about doing this with much larger molecular systems, but then this experiment, which was not done very long ago, essentially demonstrated to us that if I control light that is incident upon molecules, I can control the way in which they break apart or chemical reactions can happen. So in that sense, essentially, quantum dynamics, these electrons are quantum objects, they essentially, their life cycles can be controlled by laser pulses. I'm not really going into all the technical details, but there is one other experiment that you have actually learned in your physics courses, which is the underlying principle for why this is happening. Essentially, there are two pathways. There is a red arrow vertical and going this way. There is a red arrow that goes up and slides down. So there are two pathways in which this molecule can break up, and what we are seeing is a sort of Young's double slit experiment happening in some other domain. So this sort of interference actually helps us to control the way in which molecules can break. So that is essentially the lesson that we learned from such an experiment. And without going into too many details, I'm just calling on your intuition to look here that in this particular plot, we see fringes in some particular space. We can discuss that more in maybe a one-on-one conversation, but this is very much like what happens in a Young's double slit experiment. So lasers can actually help you perform Young's double slit experiments on molecules in the time domain and perhaps actually much, much more. Okay, now how fast can this dynamics go? So this is the Bohr model of the atom. This is not very accurate, but it gives us a sense of what is happening. What is the size of the orbital, okay, or the orbit of an electron inside a hydrogen atom? You know this is the Bohr radius. This is half a nanometer. What is the velocity of the electron? There is a very nice number, 1/137, and this is again a KBC question. So if you are ever asked for a crore, what is the velocity of an electron in hydrogen atom? Just divide the speed of light by 137. That number 137 is not changed for many lifetimes, and it will probably never change. So that is the velocity. Now if you take the orbit circumference and divide it by the velocity, you get a time. That is the time that is the year in the life cycle of an electron that is going around in the Bohr orbit. Again, I'm using a very classical picture. It is not really that electrons go about in orbits, but these denote the so-called expectation values in quantum mechanics. So there is a sense of realism there. So the orbit time of an electron is 24 attoseconds. An attosecond is 1 followed by 18 zeros in the denominator. Okay? The age of the universe is 1 followed by 18 zeros in the numerator in seconds. Okay, so with these kind of pulses, we essentially have, again, a Fourier transform relationship. If a pulse is wide, its frequency content is narrow. If a pulse is short, its frequency content is wide. Okay, this is again something that we know. And we can produce pulses in the femtosecond today, also in the so-called attosecond domain. Now, indeed, how are these so-called attosecond pulses produced, which we can produce, we can control, we can use them to make atomic and molecular movies and much more. They are essentially produced by taking femtosecond pulses. Femtosecond pulses happen to be more often than not in the near infrared. This is for technical reasons. The most popular wavelength for producing femtosecond lasers up till now is 800 nanometers. That is because of another gemstone. Sapphire actually is the gain medium or the active medium for these femtosecond lasers. Now it is moving towards 1 micrometer for other technical reasons. If this is focused into gas cells, then you get a combination of the infrared pulse and, of course, pulses in the extreme ultraviolet, which are the so-called attosecond pulses. Once again, this is something which we can once again discuss one-on-one, or maybe you can find a lot of information about this on the web if you're that curious. Okay? So I will once again refrain from going into very technical details, but maybe for a more interested physics audience, I would like to point out the fact that the process that essentially produces these attosecond pulses from femtosecond pulses is essentially a process of generating higher and higher harmonics. There are materials. One of the first experiments to be done with the ruby laser was to take the ruby laser, focus it into a crystal. The ruby laser was radiating in the infrared and produce green light from it. So infrared is beyond 800 nanometers. Green is 500 nanometers. So the frequency of light got doubled. So I can make it 10 times, I can make it 20 times, I can make it 30 times. This process itself is a very interesting one. And when I make it about 30 to 40 times, photons with 1 electron volt of energy in the infrared have been converted to photons with energies of about 30 to 40, 50, 60, even 100 electron volts these days. And the optical cycle at 100 electron volts is 10 to the 18 cycles per second. Okay, so we can conceivably make much shorter pulses in the sub-femtosecond domain as well. So now an apples to apples comparison, electronics versus photonics. What is this curve called? The curve that tells you that the speed of electronics essentially doubles in every 2 years. What is that called? It's again quiz trivia. It's Moore's law, right? And can you see this technology, photonics? It's faster than Moore. And this should be much more important, except it's not in our cell phone. Had it been, our lives would be probably very different. I don't know if they would have been better though. Okay? But then today we can produce the briefest possible processors that mankind can produce as of today are in the sub-femtosecond domain. Now you can ask me a very challenging question. If these are the shortest events produced by man, how do we measure them? Okay? How do I measure these? For example, in this clock over here, the minute hand is keeping time of the order of hours, right? The seconds hand is the hand that's keeping time for a minute. So now who is keeping time for the seconds hand? Okay, in a digital device, there is something which is doing stuff on the order of a millisecond or lower. So that's keeping time for the seconds hand, right? So this is the shortest event produced by man. So who's keeping time? Okay, I'm not calling for divine powers, but who's keeping time? If you visit our lab in IIT, we can show you how this is measured. Okay, this is very much possible. It's intimately related to another question. If I have a signal from outer space, if I detect it, how do I know whether it constitutes a signal from a native civilization of extraterrestrial beings? I don't know their language, right? Can I know something about it? It's a very interesting question. You must read about it at some point. It involves some very nice physics, but let's go beyond that. But then the question is, we have very short pulses. Can we actually realize an oscilloscope at these native frequencies of 10 to the 15 hertz? This was a question that was, to use an American phrase, an elephant in the room for a long time. Okay, what prevented this from happening until it actually did was the following. We are students of physics, right? So if I take any light field that obeys Maxwell's equations and the wave equation, and if I integrate this light field from minus infinity to plus infinity, what do I get? I always get a 0. Why is this significant? This is significant because while light oscillates very fast at the frequencies of petahertz, all the poor detectors that we have, all photodiodes for that matter, cannot respond to these frequencies. I'm speaking at about 3 kilohertz and my microphone is able to respond at 3 kilohertz, whereas this photodiode cannot respond to that. It basically integrates, or the electric field, it responds to the energy that is present in the field. Okay? So if this is the case, I can never discern the shape of this electric field. Right? There is no device capable of oscillating at that particular frequency. So can we beat this actually limit set by Maxwell? Even using slow detectors? Yes, we can do that. Can I differentiate between these two pulses? If you look at them carefully, at the peak of the dotted line, the bold line has also a peak, whereas in this case, at the peak of this dotted line, the bold line does not have a peak. So technically speaking, these two electric fields have different shapes inside the same pulse. Can I distinguish them? If I can, then I can actually, this is equivalent to making a petahertz oscilloscope. This was realized only in 2008. How was this actually realized? Maybe you can, it's a very readable paper. If you're an undergrad in physics, and I would say you must read it, and please do it on your bed because it calls for a lot of imagination. Okay? So what do? If I can somehow chop off all the other unnecessary stuff in between and make a detector that is sensitive only to the peaks above a certain cutoff, then indeed I can count in some sense the number of peaks that are there in the upward direction and the number of peaks that are there in the downward direction. This, if I introduce a threshold in my detection and do this, I will actually be able to discern even the shape of these electric fields. Okay? So for this, it is essential that you have a nonlinear process doing the magic, doing the detection. Linear detection will not work. That is what this particular integral tells us. While linear detection does not work, a nonlinear detection process indeed can do this, and we can indeed determine the shapes of of electric fields if we do such a thing and realize a petahertz oscilloscope. And how was this oscilloscope done? I maybe have about 10 minutes, which is possibly sufficient time. Again, for the curious physicist, the engineer, and the intelligent man over here, or lady, this is how a petahertz oscilloscope was realized. You have here a red electromagnetic wave, which is a femtosecond pulse. This oscillates on time scales of 10 to the 15 seconds. The blue thing here is an extreme ultraviolet pulse, which has a duration of about half a femtosecond, or 0.3 femtoseconds. Now, in order to get some signal out, I toss in a few atoms. These are few atoms of rare gas, typically helium, argon, neon, krypton, or whatever. In this case, I think it was xenon atoms. What happens then is the following. This extreme ultraviolet pulse, okay, can be very, very precisely positioned in time relative to the red curve over here. Literally how this picture shows us this to be, okay? What does this do? The extreme ultraviolet pulse releases electrons from this group of atoms. These electrons come out from their parent atoms and they are sort of around. But is the space around empty really? No, it is not. There is the red pulse which is oscillating, and this is an electric field. Now, if I ask the question, what is the momentum of an electron in such a field? Okay, then a classic physics textbook like Landau and Lifshitz, or once again, you can ask your teacher, would tell you that this is mass times velocity, the mechanical momentum with which, say, I'm moving right now, plus the so-called vector potential of light. What is the vector potential? It's essentially a quantity that's introduced by physicists whose derivative is the electric field. So the true momentum of the ever has had access to. And one of their goals is to reach this limit where you can focus down a laser pulse and break down vacuum, that is, create an electron-positron pair, okay? And also induce even nuclear reactions. Even as of today, we can induce nuclear reactions even without such very intense lasers. This is with 800 nanometer visible, 800 nanometer or 1 micrometer lasers with visible light, indeed. No gamma rays, no X-rays. Absolutely, yeah. Just very, very high order nonlinear physics. And to give an idea of, at the end of the day, if I want to use my laser energy to do science like this, I should be able to couple energy from light to matter. How do I do that? Already my colleague alluded to so-called plasmon resonances. When you drive a group of electrons in materials, they perform oscillations, which are driven oscillations, and this has a natural frequency, eigenfrequency, as we are called, as we know from undergraduate physics. If the driving frequency of the laser, which is little omega, matches the natural frequency of the system, very efficient energy transfer can take place. And in my PhD, I kind of showed that in an aggregate of helium atoms, I can actually couple in something like 1 million electron volts of energy using laser fields where each photon carried only 1 eV of energy. So such very, very high orders of high energy density matter can be indeed produced. And people now have taken advantage of this and produced electron beams with and ion beams with energies that are humongous. There are several million electron volts. Okay, so CERN, of course, has TeV, or tera electron volts, 10 to the 12 electron volts of energy in the beam. Lasers are not yet there, but this is a result for accelerating protons, which are or electrons. One can do with all sorts of charged particles. So they can be made to gain very high kinetic energies from these fields. The principle of that is actually surprisingly very, very intuitive, very, very classical. It happens on ocean waves. Do you see what this guy is doing? So he is essentially climbing up this big wave and he is sliding down like a kid slides down on a slide, right? Using that, one can produce humongous energies, and this is called so-called wake field acceleration. If you, for example, look at this, this is one of the biggest waves perhaps people have surfed on. People are on the rooftop of a building and they are looking at this this guy on the ocean floor, and he is essentially taking advantage. So this is exactly like an electron surfing a plasma wave that's created in very special conditions. And indeed, the main takeaway lesson is that the surfer cannot gain by himself a lot of kinetic energy. But here, I'm able to transfer the energy in the wave to the surfer. The surfer is taking energy from the wave. Okay, there are special conditions required for this. That is, he must enter this boom of the wave at the right time. This is exactly the physics of this problem. And indeed, this is being done in several labs. And if that is done, you can indeed produce protons of maybe 150 eV or so, or 200 eV, or 200 milli eV, not eV. There's a very, very practical application for this, which I alluded to earlier. If, unfortunately, somebody has a tumor, for example, in his or her head, then the conventional method up till now is to use X-rays to burn away the tumor. X-rays are focused into the head, but look at what X-rays do. Dose is equivalent to damage. So the dose of X-rays, actually, if the tumor is present at this point where my red dot is, it is going to damage the tissue all the way till it reaches the tumor. If it is in somebody's brain, you're taking away life functions and quality of life, and you may keep a person living, but he or she may not be able to do too much after that. Whereas charged particles have a beautiful property. Charged particles have a very nice property that if you control their energy, you can control the depth at which they deposit maximum amount of energy. This is called the Bragg curve. This is a very famous Bragg peak. Indeed, to do this here until now, we need an accelerator that is literally the size of a football field. And this therapy is so expensive that in the whole of Germany, there is just one. The patient cannot pay for it. The insurance companies cannot pay for it. So the government alone can pay for this. So can you really imagine such a technology coming to India would be unforeseeable. A limited version of that, I said, is coming in here somewhere. But if such technologies have to become affordable, then it is very, very likely that these ultra-intense modern lasers are going to do that. Now, talking about damage, you can use femtosecond lasers to make very controlled structures in materials. And that material can also be a cell. Another Indian name, Mani Bhaumik. He used excimer lasers to perform surgeries in the eye, corrective surgeries. State-of-the-art corrective surgeries actually are today being done by femtosecond lasers because they can do very, very fine, precise cutting. Okay, they can do very fine, precise cutting with almost no damage to the surrounding tissue. That's a unique facet of femtosecond pulses. So one can indeed do eye surgery and so on, and also make these kind of funny sub-micrometer structures if you wish. But just to prove that these lasers can cut without depositing heat, they actually deposit a very tiny amount of heat. This is actually a structure made on an explosive. So if you deposited heat, this would have exploded and we wouldn't have had these lines cut on the explosive. This was a demonstrative experiment done by somebody. So such very precise patterning can also be done. And maybe I'll close with this. In our own little lab, we have a moderate laser with which we can study laser plasmas, and our colleagues in engineering especially, they're very interested in making very fine structures for lab-on-chip applications. This is actually a big boon in that if that can actually be realized, you can see how fine this structure can be. And with all that, I must say, from the first Nobel Prize in 1999 for femtosecond science, given to Ahmed Zubail, all the way up to this remarkable prize this year, almost 20 years hence, only tells us that there is not only plenty of room, but there is also plenty of time at the bottom. And all of us here are invited to essentially join the ultrafast revolution in the ultrafast world. If you're more curious, of course, please do drop us an email. We even have some project positions for students who wish to engage in such research. With that, I would like to once again thank the organizers for this wonderful opportunity, and you for patiently sitting and listening for now what is 2 hours. Thank you.